We're now going to focus on part 2 of our lesson that describes method groupings in the Java Completable Features API. Again, recall the reason we're having this discussion in the first place is there's 60+ methods in the Java Completable Features API, and so we don't want to have to try to digest all of them in one fell swoop, but instead we break them up into these little groupings. Previously, we talked about basic methods, factor methods, and completion stage methods. We're now going to round out our discussion with focus on exception methods and so-called arbitrary-arity methods. So let's start first by talking about arbitrary-arity methods. And arity is just a fancy schmancy name for the number of parameters that is accepted by a method or by some kind of operation. So you're probably familiar with the concept of a unary operation, which has an arity of 1, like unary minus or unary plus. You're, of course, also familiar with binary operations, like plus, minus, divides, multiplies, which take 2, binary, arity. There's even 3 trinary operators, like there's 3 operand operators, like the question mark colon operator in Java, the so-called ternary operator, and so on. So that's what arity means. So it stands to reason that an arbitrary arity method can take an arbitrary number of parameters, and that's exactly what these methods do. Now, there are 2 of them. And the purpose of them in the Completable Features API is to process a bunch of completable features in bulk or en masse by combining all those multiple completable features into a single completable feature that then can be triggered reactively. And there's 2 different models of this, or 2 different methods that do this. One is called all of. And that gives you back, when you call it, you pass in an arbitrary set of completable features, or an arbitrary array of completable features, or list of completable features. And all of converts that arbitrary array of completable features into a single completable feature that, when triggered, indicates to the caller that all of those completable features that it has been handed before have all been triggered. So it's a way for one thing to wait for many things. And it doesn't really wait. It's one thing to get the results of many things. So you get back a completable feature, so that doesn't have to block either. So you can have one non-blocking thing that waits or is used to get the results, triggered, I should say, reactively when all the other things finish. So that's all up. And it stands to reason that there would also be another method, which is triggered when the first of an arbitrary array of completable features finish. And that is called any of. So we have all of, which waits for everything, or I keep using the word wait, it doesn't really wait. It gives back a completable feature that will be triggered when everything's done. And we have any of, which gives back one completable feature that will be triggered when the first of those things in that array complete. Very, very, very powerful mechanisms. And the basic reason why they're so powerful is they help to make the programs more responsive by not blocking caller code for parameters more than 2. So if you saw when we talked about the completion stage methods before, they had a couple of methods or method families that could wait for both of something to finish or either of 2 things to finish. This can be used to wait for n of things where n could be greater than 2. It could be 2, of course, also, or it could be 1 for that matter, but you typically use the arbitrary arity methods when you have a bunch of stuff to have to deal with. One of the tricky aspects, however, of the arbitrary arity methods out of the box is they're very complicated to program directly and are best served by defining, or best used by defining some kind of a wrapper. So it's kind of like the Gordian knot, which is complicated, so you're better off to hide it with some nice little abstractions. And we'll take a look at these things. And most commonly, they're abstracted by using some kind of collector. And I've alluded obliquely to collectors over time recently, and you'll see how they work. They're very cool. They make this complexity just disappear in a much cleaner model. The next grouping, and really the last grouping, are the exception methods. And they're necessary to handle exceptional conditions that can arise at runtime in the context of an asynchronous program. And you might ask, well, what the heck do we need that for? We already have exception handling. Why does that matter? Well, it turns out that the way you handle exceptions in an asynchronous program is quite different from the way that you handle exceptions in a synchronous program. With a synchronous program, you typically have a try-catch block. You make a method call that will call the calling thread to block or wait until the computation is done. And if an exception is thrown while that computation is running, that will be handled by the catch clause portion of the try-catch block. Pretty standard stuff. With an asynchronous model, however, you invoke the call, and then the calling thread goes off on its merry way to do whatever the heck it feels like. And if something goes wrong, that caller thread has long since disappeared, and the callee needs to figure out how to handle the exception, not the caller, because the callee is running in this asynchronous context. And so for that reason, there's a slew being like 6 or so, asynchronous exception handling methods. And I only list one here, and it's not even the best one, but there's basically handle, and there's an asynchronous version of handle. There is an exceptionally method and an asynchronous version of that, and then there's also one called when complete. And we'll talk about those when we get into that in more detail. But basically, these methods handle exceptions that run in a context that's not the caller's context. And the purpose in the context of the wonderful reactive programming principles is that these exception handling mechanisms make your programs more resilient by handling erroneous conditions and erroneous situations gracefully without having your program crash, which causes all kinds of problems, as you might imagine. All the methods that we've talked about, be they completion stage methods or factory methods or basic methods or whatever, they're all implemented internally using a message passing framework. If you take a look at the source code of the Java Completable Futures framework, which is really fun, and we'll actually take a look at part of it later, you'll see that it basically creates messages. These method calls create messages, and they get passed around and queued up and run and so on. And the reason for doing this is to make things more loosely coupled, be able to take the messages and run them on whatever core is available at the time, to try to isolate things so that one failure doesn't cause the whole thing to come crashing down, and to some extent to give you location transparency, although location here really means which core you're running on, not which computer you're running on. And internally, various Java thread pools can be used to process these messages. So cache thread pool, fixed size thread pool, work stealing pool, the common fork join pool, for example, those things can be used to process these messages. So that is the fourth principle of reactive programming, is the fact that we're doing things with message passing. So that's the end of our discussion of groupings of methods in the Java Completable Futures API. Now, at this point, you're much better prepared to start doing your programming assignment, but we still haven't really delved deep enough into the mechanisms of programming. We've just talked about the concepts and given you some guidance on how to orient those things in your head so you don't get overwhelmed with the complexity of 60+ methods in one class.